Hi, we want to talk about normality. Normality is a useful term in dealing with acids and bases because it takes into account the number of hydrogens and hydroxides that different acids and bases have to contribute to a reaction. Normality equals what we call the number of equivalents per liter of solution. What's an equivalent? Well, it's best to show that by example. An equivalent acid is the amount of acid required to produce 1 mole of hydrogen ions. So, 1 mole of hydrochloric acid produces 1 equivalent of hydrogen ions because there's only 1 hydrogen here to give up. 1 mole of sulfuric acid has 2 hydrogens to give up, so therefore it provides 2 equivalents of hydrogen ions. 1 mole of phosphoric acid has 3 moles of hydrogen to give up, so it provides 3 equivalents of hydrogen ions. And the same thing happens with bases. The equivalent base is the amount of base required to produce 1 mole of hydroxide ions. So, 1 mole of sodium hydroxide only has 1 mole of hydroxide ions to give up, therefore it's only got 1 equivalent. Calcium hydroxide has 2 hydroxide groups to give up, so therefore it produces 2 equivalents of the hydroxide ion. And aluminum hydroxide has 3 equivalents of hydroxide ions. So, therefore, the more hydroxides you've got, the more equivalents you have, which makes you a somewhat more voluminous acid or base. Another way of looking at this is that normality equals the equivalents per liter. So 1 molar hydrochloric acid is equivalent to 1 normal hydrochloric acid. 1 molar sulfuric acid, because it has 2 equivalents of hydrogen for every liter, it is 2 normal sulfuric acid. So therefore, 1 mole of sulfuric acid can neutralize twice as much base as 1 mole of hydrochloric acid because it's twice as strong or twice as concentrated. Thirdly, 1 mole of phosphoric acid, because there are 3 hydrogens for phosphoric acid to give up, yields 3 normal phosphoric acid. So therefore, 1 mole of phosphoric acid can neutralize 3 times as much base as 1 mole of hydrochloric acid. So therefore, 1 molar phosphoric acid is really 3 times as concentrated as 1 normal hydrochloric acid. And likewise, we can do the same thing with the bases, only we're looking at equivalents of hydroxide groups. Let's go to the next page. There's another term we can use called equivalent weight, where the molar mass of a acid or base is the sum of the atomic masses of the atoms that compose it. Equivalent weight is similar in that it is the grams of that particular acid or base per equivalent. A more complicated way is to say that we just take the molar mass and divide it by the number of equivalents. This is the definition you usually see in books. This is the one that I use. So what you have to do is think of it in terms of molar mass divided by the number of equivalents in that acid or base. So sulfuric acid has 2 equivalents per mole. Therefore, 1 mole of sulfuric acid has a mass of 98 grams per mole. You should be able to calculate that from 2 hydrogens of sulfur and 4 oxygens. So therefore, the equivalent weight of sulfuric acid is 98 grams divided by 2, or 49 grams per equivalent. To spell it all out mathematically, sulfuric acid has a molar mass of 98 grams per mole. It has 2 equivalents per mole, so that's why we divide by 2, makes these moles cancel to leave us with grams per equivalent. And so the equivalent weight of sulfuric acid is 49 grams per equivalent. Here's one to do on your own. See if you can figure this out. What is the equivalent weight of citric acid? First thing you got to do is write the formula. I'm giving it to you here. Because there's 3 hydrogens up front, that means there are 3 equivalents per mole of sulfuric acid. So we determine the equivalents per mole, and your answer should be 64 grams per equivalent. See if you can work that out. Might want to pause here. Good. Did you get that? I'm happy for you. Let's do an example. How does all this work? For instance, let's say we got a solution of sulfuric acid that contains 86 grams of sulfuric acid per liter. You want to calculate the normality. Let's put a period in there. So we take our 86 grams of sulfuric acid per liter. Now, since we're working in grams, it means we got to change it to moles. Yep. So I divide by the molar mass of sulfuric acid to get the number of moles of sulfuric acid. Now, I know for each, that cancels grams. I'm left with moles. Now I have to get two equivalents. So we divide by we multiply by the number of equivalents per mole. Moles cancel, leaves us with two equivalents. So the units we're left with is equivalents per liter. Hey, equivalents per liter equals normality. So you take your calculator to it, you should get 1.8 equivalents per liter. Equivalents per liter equals normality. Another example, stoichiometry problem. What volume of 0.075 normal potassium hydroxide solution is required to react exactly with 0.135 liters of 0.545 normal phosphoric acid? Now, the cool thing about this is if you're using normality, you don't have to write the equation, because one equivalent of hydrogen ions is going to react with one equivalent of hydroxide ions. So we don't have to look at molar ratios. So we're starting with 0.135 liters of 0.45 normal phosphoric acid. Why am I starting with that? Because I have the most information about the phosphoric acid. So we start with the liters, because there's nothing to divide here. We then multiply by the normality, which is in equivalents per liter. Notice how liters cancel. Then, since 1 mole of hydrogen ions cancels out with 1 equivalent of hydroxide ions, these cancel out. And here we use the normality of potassium hydroxide, because it's 0.075 equivalents per liter. The equivalents cancel, and hey, we're left with liters. That's what we're looking for, and if you take your calculator to that, it's 0.081 liters of KOH. So that should give you an idea of what normality is about and how we use it to solve acid-base neutralization reactions. Make sure you come up with a few questions to ask me tomorrow while we try some other problems.